A very good day to all the participants. Today we are going to discuss about the regenerative feed water heating system and the various HPLP heaters used for that purpose. As you know that heaters are utilized to exchange heat, and there may be closed heaters or open heaters. But in power station, the heaters which are utilized in the water steam circuit for the purpose of regenerative feed water heating, they are utilized in two segments. One is in the feed water heating segment, another is condensate heating segment, and both these segments are together contribute to the regenerative feed water heating system. In coal to electricity generation process, we have seen how water is converted into steam with the transfer of heat in the water, and this steam is utilized in the prime mover like steam turbine to generate get the work output, and naturally this steam heat energy is converted into useful work. As we see in the Rankine cycle, the useful heat value of the steam can be increased more with the operating pressure and more temperature, so that specific heat capacity of per unit steam can be utilized better for better work output and work ratio. But the problem is that if we utilize the entire heat available for expansion in the turbine, then at the end of the expansion, the exhaust steam is cooled down, condensed back into the turbine condenser by exchanging heat with the circulating water system. So naturally there is a quite significant amount of heat lost with the circulating water system as a part of the process, and this loss of heat can be minimized with the introduction of regenerative feed water heating system. And for that reason only, to increase the thermodynamic mean temperature of heat addition, we incorporate the regenerative feed water heating system as a part of modification of the Rankine cycle for better output of energy and efficiency enhancement. As we find in the basic Rankine cycle operating in subcritical regime, the heat addition takes place in the water in three phases, and there are distinct phases of your latent heat addition, superheat addition, and we have sensible heat gain. So naturally these three phases of heat addition is there, and all the heat additions are taking place at constant pressure. Now whenever we want to increase the specific heat capacity of steam, we can continue to increase the temperature of superheat, and as well as we can increase the pressure. But both these processes has the limitations, and due to those limitations we have to see how we can improve further beyond these two enhancement process by regenerative feed water heating system. There may be opportunity of improvement of cycle efficiency by lowering the condenser pressure, but if we continue to reduce the condenser pressure, the for as you know, the condenser pressure effectively is dependent upon the process of condensation, and condensation itself is dependent upon the amount of heat transferred in the circulating water system. That means if we want to reduce the condenser pressure, naturally we have to give more circulating water flow across the condenser, so that will require more pumping energy. So that so at a particular level, when the condenser pressure, if we want to reduce further, that is not economical in context of in totality with respect to CW pumping energy consumption. Increasing the superheater temperature is having a direct impact on the cycle efficiency, but superheat temperature is dependent upon the metallurgical limit of oxidation of the tube material. So we can maximum go up to the design material temperature within the oxidation limit of the tube material, beyond which it is not possible. So far we have maximum superheat steam temperature limited to 700 degrees centigrade, beyond which we cannot go for increasing the superheat temperature. Increasing the inlet pressure of water during the boiling of the water raises the mean temperature at which heat is added in the boiler, and that's why there is increase in efficiency. But at the same time this may causes a more quantity of moisture in the process of expansion. Quicker wetness is developed, so naturally there must be a balance. So we continue to increase the pressure in subcritical regime so long thermodynamic mean temperature increases at the point of heat addition, and when the thermodynamic mean temperature increase is not there effectively, then we are not going to increase the pressure. That's why the operating pressure of subcritical steam generator mostly found at the range of 160 158 kg per centimeter square. Reheating is the another way of improvement of efficiency of the Rankine cycle with modification. Through reheating we are having superheat addition at lower pressure than the superheater, but the quantity of available heat in the process of expansion is more, thereby we get less wetness during the process of expansion of the steam. That's why it is preferred for heat addition arrangement. Let us try to understand why we require regenerative feed water heating system. Actually, in Rankine steam cycle, in thermal power generation, when we are increasing the boiler pressure, degree of superheat, degree of reheat to increase efficiency, and reducing condenser pressure or vacuum, increasing the vacuum, that all are increasing the efficiency, but they have a natural limit in terms of boiler strength, temperature of the steam, and metallurgical limit, cooling system efficiency for condenser. So naturally, in view of that, for further improvement in the subcritical regime, we have to go for the system moderation. This system moderation is achieved by regenerative feed water heating system that improves the cycle efficiency more. Rankine cycle is more efficient where heat added to feed water by the steam blade from the turbine at point intermediate between throttle and exhaust that reduces the heat rejection in the condenser. Heat rejected in the circulating cooling water system of the condenser is the major loss for the turbine cycle, and what is heat regenerated through the feed water heaters after partial expansion of the steam is used for heating of the condensate or feed water, and that is again when this heat is transferred, the condensate is cascaded back to the condenser, that result more heat within the steam water circuit, including latent heat in the steam that remains within the cycle, otherwise which could have been lost in the CW system. So that's why it is reducing the condenser loss and improving the cycle efficiency almost by
regenerative feed water heating is the system to avoid complete expansion of the steam within the turbine and taking some part of it for regenerative feed heating system and transferring that heat within the feed water so that we can utilize the entire heat available with the blade steam, and that condensate of that blade steam is again returned back to the turbine condenser by cascading way method, and therefore we are
avoiding the heat rejection, and that heat rejection which could have been lost, that is being added up in the feed water heating system. So quicker feed water temperature is attaining to the boiling point. Sensible
In
heat
large
addition
capacity boilers
is getting
operating in
reduced
Rankine cycles
in the boiler,
subcritical regime,
and that's why it is
which
preferred
are
arrangement
having
for the purpose of cycle efficiency.
superheater, reheaters and other arrangements, regenerative feed heating arrangements, they are generally operating at the pressure of 150 to 180 kg per centimeter square with a saturation temperature around 340 degrees centigrade and superheated steam temperature plus minus 540 degrees centigrade. When this final superheated steam is expanded in the HP turbine, after expansion majority of the part of the steam is going for resuperheating or reheating, but from the exhaust of the HP turbine fast extraction is taken for the HP heater, and after reheating, when the reheated steam is expanded in the intermediate pressure turbine, during the process of expansion in the IP turbine there is another extraction taken, and that extraction goes to the second HP heater, and there are further extractions from intermediate pressure turbine to LP turbine crossover, intermediate turbine exhaust to LP turbine crossover. From there next extraction is taken, it is going to the boiler feed water tank and feed water heater, that is actually an open heater, only open heater in this system. Then there is further expansion in the LP turbine. During the process of expansion in the LP turbine, we take the extraction, 3 extractions are there, and first extraction is going to LP heater 3, then LP heater 2 and then LP heater 1. So this way we find a number of extractions are taking place from the entire various stages of the turbine, and all these extractions are adding heat in the regenerative feed water heating system, thereby improving the cycle efficiency. At the same time, we have a balance of expansion in the turbine so that we can also get the useful work sufficient to generate power in the system. So as such, specific work output of steam in the cycle decreases with the extraction, reducing the turbine work. So in this type of feed water heating, boiler efficiency may also decrease due to high stack loss as a result of high feed water temperature beyond the design inlet temperature of feed water within the boiler. Therefore, maximum 30% steam can be extracted from the turbine for regenerative feed water heating purpose, and optimization of feed water inlet temperature close to design condition at boiler. It is important to balance the amount of heat absorption in the boiler water steam circuit and how much feed water heating will be employing for the purpose of cycle improvement. So we have a distinct arrangement of regenerative feed water heating system. From condenser outlet, or rather from the outlet of the discharge of the CEP to boiler feed tank, we have condensed heating arrangement, regenerative heating arrangement of the condensate, and from the boiler feed tank to the HP heater discharge we have feed water heating arrangement. So these together constitute the regenerative feed water heating. Let us now try to understand the impact of regenerative feed water heating with reference to a practical application. When a system is running with regenerative feed water heating system and when there is no feed water heating system. This schematic layout is a 75 megawatt pulverized coal-fired power generation unit, and they are generating steam in a radiant natural circulation, single drum, balanced draft, dry bottom, front fired boiler, and there is auxiliary fuel used is oil and primary is coal fired, primarily it is coal fired unit, and the steam generated is superheated steam at 320 degrees centigrade, and the steam is expanding in the HP turbine. The part of the HP turbine, exhaust steam blade, steam is blade from the HP turbine exhaust, and that steam is going to the HP heater 1 for regenerative feed water heating, and this extraction is uncontrolled extraction to meet the final feed water heating temperature demand. The major amount of HP turbine exhaust is going for IP turbine, and HP heater 1 is heated with the extracted steam before entering the IP turbine. The extracted steam is also used for heating the boiler feed water tank attached to deaerator, which is the only you can say direct contact open heater arrangement. The IP turbine exhaust steam is used for heating the condensate in the LP heater. The major part of IP turbine exhaust is further expanded into low pressure turbine, and this is discharged into condenser hot oil. And there is another heater that is called vacuum heater, which is heated with the extracted steam from the 7th stage of the LP turbine blading. And again, condensate of LP heater is cascaded to vacuum heater, and from condensate from vacuum heater is cascaded back into the hot oil, feed water in the hot oil, so condensate in the hot oil. So there are flash boxes and gland steam condenser and drain coolers through which the cascading system is there. Condensate feed water pumped by condensate extraction pump after passing through vacuum heater and low pressure heater is fed into the deaerator attached to the boiler feed tank, from where suction is taken from for the boiler feed pump. The BFP discharge is passed through the HP heater 2 and HP heater 1 successively before moving to the feed water control station for the boiler economizer inlet. Now the condensate of HP1 is cascaded to HP heater 2, and subsequently it is fed into the boiler feed tank, and this way we are having the regenerative feed water heating, and this schematic layout we are trying to analyze it with the specific quantity of steam flow, and there is a thermodynamic table attached with the pressure temperature parameters with reference to specific process points, and these are discussed in the subsequent slides. So we find there are 5 extractions from the 75 megawatt unit turbine, and providing uncontrolled steam flow to 2 numbers of HP heaters, U-type HP heaters, 2 numbers U-type LP heaters, and 1 extraction to deaerator, that is directly condensing type. The regenerative feed water heating cycle starts from the condenser at low pressure and ends at economizer inlet at high pressure. So for regulating the feed heating of condensate, 5 extraction points are provided from various stages, which are shown by asterisk marks. One extraction is taken from HP turbine exhaust, termed as extraction number 5, which is going to HP heater 1, which is shown by green button. 3 extractions are taken from IP turbine, termed as extraction number 4, that is feeding to HP heater 2. Extraction 3, that is going to the boiler feed tank, open heater, and extraction 2 from IP to LP crossover pipe to LP heater. So these are shown by orange button, yellow button, and there is a lowest pressure extraction, extraction number 1 from LP heater, which is going to vacuum heater, LP heater number 1, that is shown by orange button. So this is the arrangement for 75 megawatt unit extraction. HP heater 1 extraction is taken from HP turbine outlet line. This line consists of one non-return valve and one gate valve. The NRV closes under turbine trip condition, and it also closes on heater level when it goes high, and set value is there, and this is to safeguard the turbine from water ingress. There are isolating valves also that closes due to high heater level, water level, and primarily these are provided to safeguard water ingress. And there is also drain valves, and these drain valves are provided in the drain line, and that actually gives the cascading line connection, and they are utilized according to the heater level. HP heater 2 extraction steam line is provided with pneumatically operated NRV and gate valve. NRV closes under turbine trip condition primarily to prevent overspeeding of turbine, and it is also closes on heater level going high, and to prevent ingress in case of heater level, ingress of water in the turbine in case of heater level goes high. A drain line is also there for extraction with isolating valve, motorized isolating valve, so that we can maintain the heater level according to the requirement. The third extraction is taken from IP turbine, and this extraction steam is used for deaerator pegging as well as for heating the boiler feed tank water. Extraction line is provided with one NRV and one motorized isolating valve. Extraction number 2 is taken from cross-wound pipe inlet to LP turbine and is connected to LP heater number 2. This line is provided with electrically or pneumatically assisted NRV and a gate valve. And there are some permissives according to which this extraction valve opens, and check valve will trip if the permissives are not all permissives are available. And these permissives are LP drip level not very high, secondary oil pressure is not low, turbine not tripped. There are two drain valves, drains are provided in this extraction line with motorized valve, and this LP heater is placed just before boiler feed tank inlet. First extraction is taken from LP cylinder expansion steam after 7th stage. This extraction line is provided with an isolating valve. There is no NRV provided in this line, and this is actually supplying the steam for regenerative feed water heating in the vacuum heater, and they are placed just before LP heater. So we find the basic feature in the 75 megawatt units of Durgapur Projects Limited regenerative feed water heating system. Though these systems are nowadays demolished, but these are the system present there. The two types of feed water heaters were provided in condensate and feed heating cycle. The heaters which are placed in feed cycle, that is after BFP discharge and where water pressure is high, are called high pressure heaters. The extraction pressure and temperature for these heaters are also high. Two numbers of HP heaters are provided in 75 megawatt units. In 660 megawatt we find 3 HP heaters are there. The heaters which are placed in the condensate line and where water pressure or condensate pressure is low as well as extraction steam pressure is low, temperature are less, is called low pressure heater. There are 3 numbers of LP heaters provided in 75 megawatt units. They are by name deaerator heater, LP heater and vacuum heater. The presence of air in heaters deteriorates its performance. To remove this air, all the heaters are provided with vents, so heater shell can be air can be removed from the heater shell. LP and HP heater vents are individually taken to condenser, and deaerator also connected to vent line. So there is orifice, and through orifice and regulating valve, the vent flow through vent is restricted. Additionally, HP heaters are provided with vents for startup purpose to remove the air as well as to prevent any formation of vacuum when it is not running, heater is not in operation. The deaerator vents discharge to atmosphere. This vent line has been provided with a globe valve and orifice. Deaerator is provided with motorized globe valve for startup also. So all these vent lines are utilized according to the requirement of startup, operation and shutdown of the units. Let us now discuss about the heater drain system, which is very important, particularly to maintain the level of the condensate within the heater after heat exchange, as well as to prevent any ingress of water within the turbine. During normal operation, all heater drips are cascaded from HP heater to next lower pressure heater. HP heater 1 drip is cascaded to HP heater 2 through a NRV, and then drip from HP heater 2 is cascaded to deaerator through control valve. HP heater 1 drip is also individually cascaded to deaerator if HP heater 2 is out of service. Similarly, drip from LP heater is cascaded to vacuum heater, and finally drip from vacuum heater is taken to condenser through drain cooler and LP drain flash tank. In case of high level of any heater, drip from the heater is taken directly to condenser through drain flash tank. HP heater 1 and HP heater 2 high level drips are fed to condenser via HP heater drain flash tank. For LP and vacuum heater high level drips, these are fed to condenser via LP drain flash tank. In case of outage of any heater, drip from the preceding higher pressure heater is also taken directly to condenser through the drain flash tank, except HP heater 1 drain, which is led to deaerator, where in case of HP heater 2 is not in service. So a feed water heater is a component designed to heat a given quantity of feed water through a specified temperature range with steam at a specified enthalpy content and pressure, and with a limited pressure loss of the feed water passing through this heater. The usual arrangement of this type of shell type heaters with shell and tube arrangement, where feed water is passing through the tubes and surrounding the tubes, heating medium is passed. The heating surface within the unit may be divided into 3 zones. They are condensing zone, desupperating zone, and drain cooling and subcooling zone. The performance of the feed water heaters can be analyzed by monitoring the terminal temperature difference and drain cooler approach temperature, the pressure drop of feed water side, and the temperature rise across the heater. To monitor this, it is desirable to carry out a simplified routine performance test on feed water heaters frequently, and this will help in identifying the level of deviation and performance of the heaters at different condition of supply of steam and feed water within the system. There are 2 important parameters which we must understand that determines the performance of the heaters at different conditions of operations. One is terminal temperature difference, TTD. It is actually difference between the saturation temperature corresponding to the extraction steam inlet pressure and the feed water outlet temperature. So this is giving, if TTD is high, that implies that there is less of heat transfer taking place, and TTD low means heater is working well. Now another important parameter is drain cooler approach temperature. It is the difference between the drain outlet temperature and feed water inlet temperature. This shows the how much quickly this heat will be approached and how much this heater condensate level will go high. So these two parameters are utilized to assess the performance of the heaters. The various possible causes of feed water heater performance deviations may be described as scale deposition on heater tubes, leakage of heater tubes, reduced feed water flow through the heaters, failure to vent the non-condensable gases or air blanketing within the heaters, and change in heater level from the operating limit. Now we shall undertake a case study where this 75 megawatt unit is running at maximum continuous rating with all the heaters in service and how they are performing in terms of requirement of the efficiency of the entire cycle, and that will be compared with when the HP heaters are taken out of service for some maintenance and other work, and how they are contributing, their absence is contributing in the total cycle efficiency when HP heaters are not available with the system. Now let us assume that 1 kg steam is supplied to the HP turbine and it has been expanded in the HP turbine, and from there we have M1 kg is extracted for HP heater 1, M2 kg is extracted from HP heater 2, and M3 kg is extracted for boiler feed tank heating. And this way, and for LP heaters, we are extracting M4 kg of the total steam. So this way, if we go on calculating, then from the previous database where we have collected all the thermodynamic parameters at various pressures at various locations and temperature corresponding to that pressure. So we find that M1 corresponds to 0.0495 and M2 corresponds to 0.0375, M3 corresponds to 0.0251 and M4 corresponds to 0.0454. So this way we get the value of extracted component of the steam in terms of 1 kg. Similarly, for vacuum heater, per kg of steam, the extraction steam is say M5, and that M5 can be calculated. We get M5 equal to 0.0301 kg, and with all this data, if we calculate the work done, turbine work, that can be evaluated, and whatever pump work by work done by BFP and CEP, that can be evaluated. From there we get net work done by turbine minus pump work. So we know the heat addition taking place from the boiler discharge condition, outlet condition of the boiler, steam entering into the turbine, and we also know the work output. So naturally from there we get the work output by heat input. From there we get the efficiency, and efficiency in this case of maximum continuous rating condition, that is coming out as 29.38, and heat rate comes out to be 12,253.2 kilojoule per kilowatt hour. So this efficiency calculation is based on thermodynamic properties of the working fluid with all the heaters in service, and considering that all the parameters are as per available conditions without checking the calibration of the individual measuring instruments. And also we are finding that this database in terms of heat balance in individual control points of the control volumes with respect to steam coming in, condensate moving out of the heaters, and feed water coming in, feed water, hot feed water going out of the heaters. Now let us try to analyze the system when both the HP heaters are out of service and we want to run the unit at 75 megawatt at maximum continuous rating without the availability of HP heaters. So in that case all LP heaters are available. That means we are having vacuum heaters, then LP heater and deaerator feed heating system, and with that from boiler feed tank through boiler feed pump, water going directly to the boiler for steaming. So naturally there is no feed water heating through HP heaters, and HP heater is both the HP heaters are bypassed. So in this condition, if we feed the steam turbine with 1 kg of steam for expansion, and if we take out the extraction steam, the first extraction is coming with the boiler feed tank heating steam. Let it be M1 quantity, and in LP heater the extraction steam quantity is M2, and in vacuum heater the steam extraction is M3. In that condition, from the control volume based heat balance, we get that the temperature conditions as well as the mass values. From there we get the work done. Work done in that case comes out to be 786.16 kilojoule per kg by the turbine work. Pump work is equivalent to 6.86 kilojoule per kg. So net work 779.29 kilojoule per kg. Heat addition remains at the level of 2799.52 kilojoule per kg. Therefore efficiency comes out to be 27.84, and heat rate 12,932.63 kilojoule per kilowatt hour. So there is a significant increase in heat rate and reduction in efficiency of the cycle when HP heaters are going out of service. Here is the list of thermodynamic properties at various parametric condition at different pressure at different locations with reference to both the HP heaters when they are out of service and we are running the unit at maximum continuous rating. So this database is utilized to calculate the efficiency as well as heat rate as shown in the previous slide. So we compared the parametric conditions and efficiency of the unit with respect to design data and operating parameters of 75 megawatt unit when the HP heaters are available with LP heaters and when HP heaters are not available, and we are trying to generate at MCR condition. Evidently there is substantial increase in efficiency when we are utilizing the regenerative feed water heating system in its full potential, and when we have a close control over steam flow, feed water flow and fuel flow, continuous fluctuation is there in the load demand, and turbine blade erosion is also there. There sometimes we find
deposition in the blade that causes the heat utilization from the steam during the expansion in the turbine. So naturally there is a variation in boiler feed water inlet temperature under different condition of regenerative feed water heating or the process of heat transfer. So final feed water temperature we need to have at the inlet of the boiler very close to the design specification, and more it is closer to the feed water inlet temperature at the boiler, we have better efficiency of the system. Typically a 10 degree Fahrenheit or 3.5 degree centigrade degradation in final feed water temperature at the boiler inlet, it is around costing 85 British thermal unit per kilowatt of energy input. There is some important parametric outcome of this experimental analysis when we have both the feed water HP heaters available and when both the feed water HP heaters are unavailable at 100% MCR condition. The feed water inlet temperature to economizer with both the HP heater available is 210.9 degrees centigrade, and it is seen that at the same MCR operation with both the heaters kept out of service, the final feed water inlet temperature to boiler reduces to 160 degrees centigrade. So this drop in feed water temperature is equivalent to a heat rate penalty of 223.4 kilojoule per kilowatt hour, which is very significant in terms of efficiency also and loss of heat value, energy conversion. So efficiency wise, if we see that due to the unavailability of HP heaters, the efficiency reduces from 29.38% to 27.54%, and heat rate increases from 12,253.23 to 12,932.63 kilojoule per kg. This picture is of deaerator with boiler feed tank. Deaerator is always placed above the boiler feed tank. Inside the deaerator we have the arrangement for deaeration. So for that we have some trays and we have water spraying arrangement, and there is pegging arrangement too. That means pegging steam is provided from the bottom of the tray through which water is coming to the boiler feed water tank. Within the feed water tank also we have heating steam supplied from extracted steam, as well as there is some pressurizing steam supplied from PRDS steam supply system. So together heating steam and pressurizing steam, there is a continuous steam supply within this location of boiler feed tank. There are also several recirculation lines as well as drain lines. So all the HP heater cascaded drains are connected to boiler feed tank, and LP heater outlet water condensate that is coming to this deaerator, and after deaeration it is getting stored in the boiler feed tank, from where boiler feed pump is getting suction, and in some of the locations we have booster pumps also. So to boost up the flow to the boiler feed pump, this is basically provided to avoid loss of NPSH. Most of the places you will find that this boiler feed tank and deaerator is placed around an elevation above the turbine floor, so that at the ground level where boiler feed pump is placed, it is getting sufficient NPSH
In supercritical units, the unit size is large, and as the units are having supercritical steaming, so naturally we have more uh, sensible heat gain within the regenerative feed water heating system. So naturally number of heaters are more in this kind of plants, and generally we find that bigger plants, they are having either single reheat or double reheat, as well as these boiler feed pumps, they may be motor driven as well as turbo driven. So in general, for 500 megawatt and larger capacity units, we find 3 HP heaters are there, and most of the cases there may be 4 to 6 LP heaters. In 660 megawatt turbo generator unit, where hot well is having connection to 3 CPs. CPs are drawing condensate from hot well, and that is passing through a gland steam condenser, processing unit, condensate polishing unit, and then LP heaters are there. There are 4 LP heaters, 2 LP heaters, first level LP heaters are placed nearby the condenser, and LP heater 2, 3, 4 is placed from the LP heater 4. Condensate is going to the deaerator. So this is the standard connection for 660 megawatt, 500 megawatt units, where number of LP heaters are at least 4 to 5. In 660 megawatt supercritical turbogenerator feed water heating system, generally the feed storage tank is connected with 2 types of boiler feed pumps. There are 2 motor driven boiler feed pumps and 2 turbo driven boiler feed pumps, and all the pumps discharge is connected with the HP heater train. There are 3 HP heaters, 6, 7, 8 heaters, heater number 6, heater number 7 and heater number 8. So these heaters are placed one after another. There is cascading arrangement, drip cascading arrangement, and drain cascading arrangement. And from here, after the highest pressure and highest temperature heater, this feed water is going through the some dissipating section to the feed regulating station, feed control station, and from there it is going to the boiler economizer zone. Now we find all these heaters which are attached to this regenerative feed water heating system, most of them are connected with uncontrolled steam flow, extraction steam flow. Some are connected with NRV arrangement, and some are connected with some globe valves or isolating valves. But the thing is that the level of extraction, the amount of feed water flow through these extracted steam heaters, naturally it affects the functioning. There may be conditions when high level is coming up, and signal then sends to drain valve to open. There may be lower chamber 3-way valves is there, and on the basis of pressure and temperature it also actuates. So it actuates the limit switch of closing, indicating the close position of 3-way valves when normal to bypass conditions may come into picture. So this way, whenever there is a condition which is not suitable for the extraction steam inlet to the HP heater, or there may be some chances of backtracking of condensate from the heater to the turbine.
So to prevent that, we have arrangement to control it by valves and drain arrangement, and these are safeguarding the entire system. So that's all on regenerative feed water heating and HPLP heaters utilized in the regenerative feed water heating system, and how they are involved in the process of improving the cycle efficiency. If you have any queries and questions, please contact me through email. I will be ready to answer your queries. Thank you. Thanks.